So hey guys, we are back with another video, and in this particular video we are going to understand about DeepSeek R1. So I think previously we already have a video around DeepSeek V3, and at the end of that video I told you guys, right, that we will be talking about R1 in detail in another video. So yeah, this is that video. I'll try to keep things as simple as possible and brief you guys about all the major aspects of the mathematics and benchmarking achievements of DeepSeek R1. Okay, let's go ahead. So first we need to understand this transition from DeepSeek V3 to DeepSeek R10 and R1. What is R10 and R1 and how do they differentiate between each other? That we'll see in the upcoming slides. So the first thing is that we had this DeepSeek base model, right? So we trained then DeepSeek V3 training using a pre-training phase of 671 billion parameters. We had a lot of new things in that, the MOE architecture, the multi-token prediction, right? And the architecture was simply MOE, and the training data was around 14.8 trillion tokens, right? And the training time was 2.788 GPU hours. So post training we had simple SFT, nothing much different, and we got the DeepSeek V3 final model. But DeepSeek R1 is built on the foundation of that is built on DeepSeek V3. Okay, so we took the DeepSeek V3 model. We started cold start fine tuning it on a small curated data set. Then we had reinforcement learning, purely the data sets for reasoning part. Then we had rejection sampling, that on a very high quality synthetic data. This data was not generated simply using normal models. Very good set of models were used, and this was manually reviewed too. Then we had data merging using synthetic and supervised data, and then final RL process. And then we finally got DeepSeek R1 model. Okay. Now coming to the difference between these two, DeepSeek R10 and DeepSeek R1. So the training approach, let's go one by one. So the R10 is purely based on reinforcement learning, but R1 is based on multi-phase, that is the supervised fine-tuning plus the reinforcement learning. There was obviously no fine-tuning done for R10, and as I already told you guys in the previous one, we have done supervised fine-tuning in above. Now the reasoning capability in R10 is very decent, I would say, not bad, but decent. But R1 is very strong than R10. It is really enhanced, and you can see in the AIME performance, right? 71% for R10, although 71% is pretty good. We are getting almost 80% performance on R1. This 9% increase is on the hardest problems, right? Now the key characteristics, it has strong reasoning, but obviously the readability issues are there because it is majorly trained for this reasoning purpose only. We don't see any supervised fine-tuning done here. And for the second model, we have better language consistency and readability. Okay. Now, what exactly is reasoning / thinking? A lot of people, when told about these terms, right, they actually think the models thinks inside itself and then answer. So usually it is still the token generation part. We usually have an XML format where you teach the model like this. Okay, for using a data set, let's say you have to add numbers 2 plus 2. So it is going to add, okay, the user is asking me, the first point is the user is asking me to add numbers 2 and 2. The first number is 2, second point, the third number is 2. Addition means summing up two numbers. So I need to sum up these two numbers and I'll come up with 4. I'm just giving you guys one example that this is how the model starts breaking down the whole problem into small steps, and then it is able to achieve an answer. Okay. Now, as I told you, they started with a cold start. There are going to be a lot of parts which I am taking from the paper itself. That unlike DeepSeek R10, to prevent the early and stable cold start phase of RL training, for DeepSeek R1, we construct and collect a small amount of long chain of thoughts data to fine tune the model as the initial RL actor. So this is where you will start seeing that DeepSeek R1 is different from DeepSeek R10. Similarly, for reasoning-oriented reinforcement learning, I said that this phase focuses on enhancing the model's reasoning capabilities, particularly in reasoning-intensive tasks such as coding, mathematics, science, and logical reasoning, because these all require a lot of thinking, right? If you're doing a mathematical or science problem, it's pretty easy. It's not easy for you to without think and answer, right? You have to think about it in multiple steps and then answer the question. Now, when we come to the difference between DeepSeek R1 and R10, you will see that after fine-tuning V3 on cold start, we apply the large same-scale reinforcement learning process as employed in DeepSeek R10. This part remains same overall, okay? But the fine-tuning was obviously different. Now, rejection sampling and supervised fine-tuning, I don't think I have to explain this much, but yeah, unlike the initial cold start data, which primarily focuses on reasoning, This stage incorporates data from other domains to enhance the model's capability in writing, role playing, and other general purpose. I think we have already discussed in some of our previous videos. Yeah. Now, reinforcement learning for all scenarios. So specifically, they have trained the model using a combination of reward signals and diverse prompt distribution. So I think we all know, right, the policy part of the whole reinforcement learning, that they have done exactly the same thing, but they have took all the scenarios here. And I think they have used, this concept, right, GRPU, they're already making the whole thing very diverse by creating multiple answers and then relatively grading all of them and then getting the final score. So this GRPO, right, group relative policy optimization. So in order to save the cost of RL, we adopt a group relative policy optimization. I think cost saving is one thing, and coming up with such an awesome solution which can help the future developers is another thing. I would appreciate it that they actually open source this whole technique. So they say that which foregoes the critical model, that is typically the same size as policy model, and estimates the baseline from group scores instead. So we'll understand these all things in detail. So let's say you have a response, right? It will go to correctly. You will check all these following things. Is it having the correct? Is the response correct? Is the length correct? Is it helpful? Is it correct format? And on the basis of all these four things, you produce a final reward. Okay. There's a possibility that three of them are good, one is not good. So 0.75, right? Maybe two of them are good, two of them are 0.1, something like that. I'm just giving you guys an example, but this is how you relatively are awarding it based on the other parameters also. Okay. So this is a typical template for DeepSeek R1 So this prompt will be replaced with specific reasoning question during training, obviously. So if you read this prompt, it's a very direct prompt, right? A conversation between user and assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in the mind and then provides the user with the answer. So the reasoning process and answer are enclosed within think tags, right? This XML format, think and /think, and answer text respectively, and thinks reasoning process is here and answer uses here. Now the user is this and the assistant has to answer now. Okay. So exactly what is this GRPU algorithm? Let's understand. Okay. So this is the typical GPU algorithm. You see, you are generating one answer, you have the reference model, reward model, and the value model, and from that you will get the KL divergence and everything. At the end, you will calculate the final score. But in GRPU, you have multiple answers produced, and you have the reference model and a reward model. I think from the DPU part, everything was shocked that we never thought about it when your own model can act as a reward model, right? But I think they are saying that they'll have the reward model. Okay. So you have the R1, R2, and RG here. Okay. So from this, you will do the group computation and you will get the final score of each one of them. I think we'll understand it more when we talk about it mathematically now. So the first step is group sampling. So I took a lot of material from an explanation from Unsloth and Hugging Face course. I'll pin down that course. You guys can go and check that out. It's a really awesome course, right? So the first part is to generate multiple possible answers for each question. Okay. So this creates a diverse set of output that can be compared with each other. Now, if you see, for a question Q, the model is going to generate, let's say, G outputs. Okay, the G output, the group size for the train policy. Okay, where G is equals to 8, where you can say that each one represents the completion from the model. So let's have a look at the example question. Let's calculate 2 plus 2 multiplied by 6. Now the outputs is G is equals to 8. So you'll have one correct, that is 14, another is 16, wrong, 10, wrong, 14, wrong. You have 8 outputs, right? So now you will notice that some of the generated answers are correct and others are wrong. Obviously, this diversity is very much required, right? Because if you want to teach your model, okay, this is correct and this is not correct, you need to have wrong answers with you too, right? How are you going to teach a model that, okay, this is wrong and this is right without having the wrong data with you? Okay, so this is the calculation, advantage calculation, that once we have multiple responses, we need to determine a way which ones are better than others. This is where the advantage calculations comes, right? So if you see here, we have this whole concept of assigning a reward to each generated response, right? So we will take the same example. We will assign a reward score to each of the generated answer based on the correctness of that answer. Okay, let's say you can have 1 for correct response and 0 for wrong response. We are not following that particular thing which I was telling you previously, right? That we will have 4 parameters. On the basis of that we will award. That we'll do maybe in future, but right now let's keep it very simple. So the key insights of GRPU is that we don't need absolute measures of quality. We can compare outputs within the same group, right? This is the best part. So you have the mean of all of them, the scores and the standard deviation, and you're subtracting it from R, right? And you're getting the particular that score for a single one, and this is how you get the score for all of them. So let's say R is 1 here, right? You take mean of all of them, you already have that particular value. You have standard deviation of all of them, you have that value. And for each reward, you already have that number, right? Let's say reward is 5 minus the mean of all of them. Let's say that is, I'm just taking an example, I think 5 is not a correct answer. 0.5, let's say 0.5 minus 0.3, that is coming as the mean. So 0.2 multiplied by the standard deviation, whatever it is, you get the final answer, right? I think it's pretty easy, right? If you guys think about this, we had the similar concept when we were studying about a physics concept in 11th standard. I don't exactly remember it, but yeah, it was quite similar to it. Now, continuing the, we have 8 responses, as I told you, 4 of which are correct. Now, the group average is 0.5. Oh my god, I was taking that as an example. So standard deviation is 0.53. The advantage value, that is 1 minus 0.5 divided by 0.53 is 0.94. And same you have the for the wrong response. So that is minus 0.94. Okay, now this, you guys are going to say that for every time the reward is wrong, we will get minus, right? But this is how you are going to teach the model, okay, that when you're doing something wrong, we are either going to reward you very, very less, no reward, or you will get penalty for it, right? This is how you teach your model. So because now that we have understood this whole calculation rules, right, they are telling us that the standardization allows the model to access each response relative performance. So this is just mathematical explanation, right, that why we are doing it. But I think I already told you guys, this is just for relative performance, right? I think you all know about this concept of grading in our school, right? In our colleges where we do relative grading. So the reason is to have a competition between good students and bad students. There's nothing such as bad students. I would say students are not performing that well, I can say, right? So then you update the policy. The final step is to use these values that we got, either they are like positive or negative, doesn't matter, to update our model so it becomes more likely to generate the positive responses, right? Not the negative ones. So the target function for the policy is this. So it's, I know it's very complicated, right? The formula is actually very complicated. This is the policy formula for this reinforcement learning. I think in WORM also you have a very complicated formula, but it's fine, right? We'll break this whole thing down. So we'll break down the maths, right? Now we have the probability ratio, right? So it's defined as pi theta of OI by Q. Now if you see here, what are you going to get from this, right? Now this particular formula is going to compare how much the new model's response, right, differs from the old model's response, because you are changing, right, while incorporating a preference for responses. Because if the value that you got from that is positive, it is going to more likely generate that response. But if it was negative, it is not going to generate that response. You don't want it to, right? So the ratio of this is more than 1. The new model assigns a high probability score to that particular response. Obviously from this formula you can get this, right? But if the ratio is less than 1, the model is going to assign a very low probability to this particular output. Okay, now this clip function, right? So we have to limit the ratio discussed above to be within I minus eta plus I plus eta, right, to avoid this drastic changes, because you don't want that the models to surpass limit of changes, like the numbers change too much every time, because you don't want your graph to go like this, something like this, right? You want small changes, because this is how you learn. Okay, in other words, it limits how much probability ratio can increase to help maintaining stability, right? So it's a basic clipping function. I don't think that there's much to discuss here, because till now we have already discussed about this part, right? This part is being discussed. So you see, when you break down this whole mathematics thing into small things, it's not at all very hard, right? See, this was the part, this was the part, this has already been discussed. It was easy as that, right? You are just calculating the ratio and clipping it, that's it. So example, if you want to take, here it is, eta is equals to 0.2. So the ratio that is coming is 0.9 by 0.5, so it's 1.8. So you clip it to 1.2, the upper limit bound is 1.2. Okay, now when it comes to, because you have 1 minus eta, that is 0.8, and 1 plus eta, that is 1.2. So you can't exceed these numbers. So because 1.8 was closer to 1.2, so that's the reason I'm reaching there. Okay, similarly, for if you want to say if the policy is not in favor of that, so you will get 0.4. But because 0.4 is too much difference, you are going to scale it down to 0.8. So yeah, now the scale divergence, I think already most of you know. I think this part we discussed, this only this part is left. So this is the scale divergence term, and I don't think we need to explain much, right? It basically this whole pi, the reinforcement learning part, right? It pre-updates the model's output, the per token loss, and this pi theta is the new model's output, right? The new per token logs. Okay, so this whole concept, right? It minimizes the model to prevent the model from deviating too far from the original behavior during optimization. Because as I told you, the whole thing is we want to learn step at a time, not you don't want this to happen, right? So in this context, minimizing KL divergence reduces the risk of the model generating nonsensical text, or in case of mathematical reasoning, producing extremely incorrect answers. Okay, so yeah. So I think calling that KL distance is defined as following. I think we already know the role of this B is beta, right? It controls how strongly we enforce the KL divergence constraint. Okay, so if you put this higher beta, right, you are imposing a stronger KL penalty. But if you're like lowering the beta, you are imposing a weaker KL penalty. So you have this you want this beta to be very balanced, right? Because if you make it too good, it can slow down the adaptation. It can actually over optimize the risk. But if you make it too strong, it can slow down the adaptation. So you want it to be somewhere balanced. So in DeepSeek math, they have put this as 0.04. Seems pretty good. Now let's take an example. Okay, let's say you have 2 plus 2 by 6. I think we all know the answer is 14, but this is the easiest example one can take, right, from a model standpoint. So you're getting 14, 10, 16, 14. This is the mean that you were getting. For correct response 0.94, wrong response 0.95. So if you see from here, right, for I think except this only you get 0.94. For all of them you will get minus 0.94. Nice. So finally we update our model to reinforce the correct responses. You get a ratio, right? I think we are here. Yeah. So you get the correct output O1 is 0.5 that you are getting from here. Okay. For the correct response you are getting here, and I think 1 is there, right? And the mean is 0.5. So the is 0.5, and the new policy then increases to 0.7. Okay, because you have this old policy that is pi theta old, and now because the ratio is come to 1.4 and you are keeping it as 0.2, so that increases range from 0.8 to 1.2. So the ratio is coming to 1.4. Okay, now look at some results, right, guys? I hope you guys understood this. GRPO is not very complex, right? If you understand it from breaking down the whole steps, just like LLM is breaking down in reasoning part, right? Making complex things easy step by step by step. It's not that complex. Now let's come to the results part. Looking at the intelligence index incorporated. So I took all this data from artificial analysis. I think Andrew G shared it on LinkedIn, I think an year back, but it's really good. So if you see, guys, here, DeepSeek R1 is standing currently at 4th position all over the world on this intelligence index, where it evaluates 7 things: reasoning, knowledge, math, and coding. I think 3-4 more things are there. And the best model is Gemini 2.5 Pro experimental, Grok 3 reasoning beta, O3 mini, and then 4th is DeepSeek R1. So, and I think then you have 5th position Claude 3.7 Sonnet. I'm currently using this model too much, right? And if you look at GPT-4, right, I can't find the March 2025 version. It's 50. It's too low, right? But if you look at the latest Metla model, it's 3.370 billion. Oh, 405 billion is not there. What? And it's at 41. Now, coming to model type, reasoning models and non-reasoning models, you will see that Gemini 2.5 Pro is a reasoning model and it's performing the best, 68. But Grok 3, being a reasoning model, is performing decent, I would say, 66. It's very close to Gemini 2.5 Pro. And all the reasoning models are, guys, performing better than other models. Think about this, right? These are all complex tasks spanning reasoning, knowledge, math and coding. These all knowledge, math and coding. When you say knowledge, you mean science. All these are complex tasks. Obviously, a reasoning model is going to perform better than a non-reasoning model, right? That is why you guys are seeing like very huge difference. But DeepSeek V3 is still giving close competition. Grok 3, DeepSeek V3 are giving very close competition to 3.7 Sonnet. And this Quen model, I think it's a Quen model or what? So yeah, you can say from this point, right, that Claude 3.7 Sonnet is the weakest model in all the reasoning models. Then you can say, because it's performing 57 and the best model is performing actually 66, 68, right? Yeah. Now again we have the open weights versus proprietary. So who can argue on this, right? DeepSeek R1 is the best model in open source. That's the best thing that they have done, that they have at least tried something new in the market, that they are open sourcing these models, and we are coming back to the open source era. Else, it's very close to Gemini, only 8 points difference, although 8 points is a lot. You can, from 8 points you can reach to GPT-4o from here to DeepSeek V3, but at least someone is trying, right? And these two models are here as stand as a hope to us that okay, reasoning models are open source. The best current non-reasoning model, that is V3, is also open source. But I think GPT-4o, the April update, right, the March update 2025, I think some people are saying that they have observed that it is even better than DeepSeek V3. Now this I won't be able to zoom, but guys, these are MMLU Pro and everything, and you guys can see DeepSeek R1 is almost in the top 5 every time, right? Although Gemini 2.5 Pro is outperforming everywhere, literally everywhere, I think, but human eval coding 3.7 Sonnet. The reason I have to get subscription, right? The Cloud 3.7 Sonnet. So yeah, intelligence versus price, the final thing. Here you will see, guys, that this index, right, it is a very good index, you'll see, because if you look DeepSeek R1, right, it takes a lot of time to think, guys. They have not measured time here, but I think they should have. Anyways, sometimes I have felt that it overthinks on things which it doesn't need to. So I think if you see here, the score is 65, and the best model here is right now R1 only, I guess, or it is O3 mini. O3 is $2, and I think it's $1, I think. So yeah, the best model in this also is R1 right now. So kudos to them. And 3.7 Sonnet, although it's not that good, but people are using it for coding, right? Intelligence is output speed, and here you will see, right, Gemini 2.5 Pro, it's the best, right? Output speed is output tokens per second, and this is the best because you want it to be as high as possible, and it is doing really good tokens per second, so it's around more than 150 tokens per second, and the score is also right 60, more than 65. So yeah, guys, that was it for this video. I hope you guys understood something new and have learned what you guys came here for. So if you guys like this video, please consider subscribing to the channel and do give me a thumbs up, right? So thank you for watching the video, guys. Thank you and have a nice day.